Hey there everyone, my name is Ryan Schul. Welcome to my channel. In this project today, I want to show you how to do anomaly detection. Okay, so anomalies are basically red flags. They're used to draw our attention towards something that we might not otherwise be aware of. Okay, so basically this could be some kind of error in the data, bad data entries. It could be typos, corrupted inputs, corrupted outputs, fraud, unauthorized money transactions, policy violations, somebody trying to game the system. These are rare but very important events. And based on these events, which typically are one-offs, they're not very common, right? But we can take decision to either modify the business if something seems to be broken, improve operations. If there's a transaction where people are trying to steal money from us, we can correct for that behavior too. Okay, so we're just looking for very unique cases of outliers or anomalies. We're going to use isolation forest in this analysis, right? So how does this even work? What is an isolation forest? You probably heard of random forest, right? This is very similar. It basically takes features randomly, selects these, and splits all these features, so you have kind of like a tree-like structure. And this is where we get the name random forest and isolation forest. All these splits look like branches on the tree, and we build many random branches from all the different possible combinations of features that we feed into the model and see what these patterns are, and then measure how easy it is to isolate that data point in the set among all of its peers. Okay, so we want to look for data that is heterogeneous, it stands out, it's different from everything else. Anything that's homogeneous is not going to be an outlier. Heterogeneous could be considered an outlier. Okay, so combination, or an example here, I'll show you in just a moment where I got this data set. It could be a very low salary for a very senior person with a very senior title. That could be an anomaly, or vice versa, a very high salary for somebody with a very low title. So it's not just high salaries, it's not just low salaries, it's a combination of different things, right? So very high salaries in an agency where most salaries are low, this could be considered an anomaly, and a normal salary at the job is just not an anomaly. That's a homogeneous part of the greater population. So I decided to do the analysis on this. I found this just a couple of days ago. It says City of New York widgets mobile redirect equals true. Now, I don't even know what this data is, but I think for our purposes, it's interesting. And at least we can start to look at some different things over here, like agency start date. This is work location, title description, and then leave status as of June 30th. Okay, and there's quite a few records here. It's over 6 million. Now, I don't think 6 million people work for the city of New York, and it says over here widgets. That sounds like some kind of weird case study or something that you might get in college. I don't even know where this data is coming from. Let me see here. Open data. Oh, I think it is legit. I'm not sure what that widget part was, but I think this is legit data. That looks interesting. I'll have to come back to that. Okay, so we have our data. We do an import, and I'm getting 50,000 records right here. It comes into us as a JSON string, and I reshape that into a pandas data frame. So this is what we have: fiscal year, payroll number, agency, the name of the person, what borough they work in, okay, leave status, salary per annum, base salary, regular hours, and regular gross and paid and total overtime paid. Okay, so pretty straightforward data. So we are going to go ahead and import the isolation forest library, do some one-hot encoding, because with everything in the machine learning world, you've probably seen this if you've seen my other videos, the machine can very easily understand payroll number, fiscal year, because that's the number. Okay, so it knows regular hours, it knows overtime hours. The machine knows all these things. It doesn't know Bronx, it doesn't know Brooklyn, it doesn't know Kilgore, or Lantha, or Chertsey Wisdom, right? So anything that is text or not numeric, we have to one-hot encode it and create that into some type of numeric feature. So that's why we need one-hot encoding, okay? So we're going to do that. All of these numeric columns are going to be fed into the machine learning algo pretty easily, right? Because these are just numbers. Anything that's not a number, we are going to one-hot encode. And then where's my one-hot encoder? Import one-hot encoder. That's not what I was looking for. I was looking for this. Okay, yeah, so it goes down here, one-hot encoding. Anything that is not numeric, that has to go into a one-hot encoder, and then we convert all of these into numeric columns, right? So we have the base salary. These are all the numbers over here. And then for column and numeric columns, we are just making sure that those are numbers. And then for any feature that's not numeric, like agency name, title, description, we go ahead and put those into our features over here. And features is showing up right here. So we're fitting the encoder using one-hot encoding methodology. And there's a couple ways to do this. You can use one-hot encoding. Categorical encoding is another way. Label encoding is another way. There's different means to the same end, but there's really different reasons why you might want to choose one over the other. There's no universally right answer for is one-hot encoding better or categorical encoding or label encoding. It really depends on the data that you're working with and what your ultimate objective is too. So I've got a video about that. You guys should check that out if you want to learn more about encoding. Okay, so let's go down here. So we have everything in numeric form. We can go ahead and feed that into the model. This is our X variable right here. Okay, we're concatenating, again, all the numerics with the non-numerics, feeding it into the model and making predictions. And you can tell that the model is isolation forced. Okay, so here we go. And okay, so DF anomaly. So this is anomaly, false, 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 false. And we're getting falses or true. So based on what the model is being trained on, and it's assigned anomaly equals 1 if it's true. If it's false, it's going to be 0, right? So do nothing if it's false. If it's true, then do something. And so far, all these are false. But you'll see that in these types of analysis, like most things are not anomalies, right? We have, in this case, let me see, I think we imported 50,000 records. Let me look at what this thing says over here. 50,000. Yep, 50,000. Yep. So we got that. And of this whole group, if we go back and look at just the anomalies, I'm taking everything that's labeled as an anomaly that says data frame anomaly. If that is set to true, I'm copying that, basically copying that over here. And then I want to look at that data. So I have 992 anomalies and 22 columns. Originally, remember, we started with 50,000 records, and we have 992 anomalies. Now we know which the anomalies are, which records are anomalies, and we can go ahead and plot that data over here. So let me refresh this chart, and we can see what the output is. Oh, it's not defined. Okay, so it didn't run some of these data frames at the beginning. You really have to do the stuff in order. And I was playing around with some other things too, so something got knocked out of the memory. Okay, so that's running. That will take just a moment. Then we can do the encoding, and we can grab our anomaly universe here and print it out just so visually we can spot what the anomalies are. I always like to do a quick sanity check with these things. Okay, and the data is in. Okay, so the model is, oh, the label encoder is running. Now the model is done. Okay, and we have the anomalies. Great. Okay, so now we can go ahead and do the plot. Let's plot this guy. Okay, and I always like to use these plotly charts. They're interactive, very dynamic. You can put the mouse over, and it shows you the details of what you're looking at, and you can zoom in and zoom out too. So I like these things a lot. So here's couple of anomalies right here, 142 with a lower salary. So these guys must have a senior title and lower salary. You can see where all the all salaries are right here, and the anomaly salaries are down here. I like these two because you can turn these on or off too. I like these plotly charts a lot. So we have 125 anomalies there, 142, 62, so on and so forth. And then we have some over here. That's why I would expect these people with a higher salary probably are going to get kicked into the anomaly bucket, right, by using isolation forest. But again, not necessarily. If you had a very high salary, then almost certainly. But if you had a very high salary and a high title, then you wouldn't necessarily be an anomaly, right? And the same thing down here. If you have a very low salary and a high title, that sounds suspicious. That sounds like an outlier. That is either a data quality issue, or for some reason, we would have to look into it. Why is a guy with a very, very senior title making very low money, or vice versa, right? So these things sometimes just need to do some due diligence. So again, I'm putting the anomalies into red, and you can see based on the job title here where the anomalies are falling. So we have anomaly label that came from the data frame, and that was given to us by the random forest, right? And then anything, again, we're looking at base salary and title description. Over here, we are looking at, let's see, base salary and just the counts. We're just looking at base salary and counts. Now we have base salary and title description. Let me refresh this. Okay, now we have everything, and everything in red is an anomaly, right? And everything in blue is normal. So you can see admin, director of social services. Okay, so we have a couple anomaly records over here. And again, I think if I double click here and then zoom out and get rid of all of these records, it gets a little bit easier to read because we have, what, almost 50,000 records that are not anomalies. I think we said 49,000 approximate were, and 992 or whatever. Yeah, 992 were flagged as anomalies, right? So it's pretty helpful to look at these charts and to see how this stuff shakes out. Oh, I just turned it off. That's why it's doing that. And again, it's not hard to set these up, right? You go to Plotly. Here's your data frame. Here's your X variable. This is the title description. Here's the Y variable, base salary. And these things are actually optional over here. You don't even need that. We want the color to be anomalies, right? So they can stand out. And that's basically it. You have a couple little controls over here. I'm tilting the angle of the text 45 degrees to make it a little bit easier to read. You have a setting that creates the background as white. If you didn't, I think they have white and dark. But they have all kinds of color templates in between as well. So you just pick what you're comfortable with and add these variables in, and you can do some really cool stuff. I like the white, so I'm going to flip back to that. Okay, so now we're looking at something a little bit different. We have agency start date, and then we're converting that to date time just to make sure everything is date time. I see this happen all the time. You're trying to work with dates, and it comes in as a string because the data type is not handled correctly or labeled correctly or whatever people do. I don't know. But if they give you a date that should be a date, but it's actually a string, you're going to have to convert these. So I like to do this just so you don't get any weird stuff. And then we can say years of service is today minus agency start date divided by 365. So then we can plot this. And again, you just have your data frame object over here. X is years of service. Y is the base salary. And the color of the dot is the anomaly. So it's really easy to set up these charts and do the plotting. And then, of course, you can zoom in and you can see all the details right here. Okay, I'm looking at this. Probably I should have added the person's name in here so we can see what these are. We can see all the reds are the outliers, but there's no person's name, so I'd have to go back and get the name column, first and last name, and add that in to make that chart a little bit better. That's probably room for improvement for that one. But okay, you know what? I'll leave that as an item to do. Before I send this out to you guys, I will add in that enhancement, but let's keep rolling here and look at a couple more things. I'll switch back and I'll add in the person's name because this would be a much more meaningful graph if you can see who these people are. Right now I can't even tell, right? We can map back to the data, but that's a lot of work. Let's just add in the names. I'll take care of that. So don't worry about that. Now we can spot misclassifier or title inflation using a couple different techniques, right? So we're looking at average title salary and grouping by title description and then base salary, okay? So we're taking the average salary and grouping by title description, and then what? Base salary divided by title average salary. So this can be the ratio of salary to title average. This is how we can compare every individual to the group average, right? So that's how we're going to know like who's high and who's low in the group compared to the entire group, and flag misclassified cases. So if high, 1.5 times higher than the average, I want to know about it. Otherwise, if it's lower, like 1/2 of the average of the group, I want to know about it. Otherwise, just normal, okay? So we're going to set a title flag over here, and you can see how this works, right? Like this guy is 2.9 times higher than the average. This guy is 1.9, so he's high, he's high, he's high. This is low. This is maybe even data entry issue or what, but they're making 30.09. I think this is dollars, right? So this probably looks like a data quality issue. I don't think this person makes $30 per year, and this one makes 280,000 per year. But that's what this anomaly detection is for, right? It figures this out very quick and very easily. This is high, this is 1.6 times, this is low, this is probably a data quality issue. So we would probably want to go back to the data source and get that cleaned up. I mean, there's a couple ways. You can just kick these out if you say this is low, but I think it's good to know about it. This seems like a data quality issue, and this one does too. These others seem fine, but again, this guy makes 1.6 times the average of the rest of the group. This makes 2 times. This is almost 3 times more than the group. So you might want to have a conversation with this person or this person's boss and say, we're paying this dude, who is this? Monique Richards. Maybe it's a lady, it's not even a dude. We're paying them 3 times more than the peer group with the same title. So why is that? Do they have a very unique skill, or is there some kind of favoritism or nepotism or what? But that sounds like it's very suspicious, definitely an anomaly, and definitely a conversation should be had about that, right? So a couple other ways to detect outliers is you use the z-score method. So the z-score looks for higher and lower thresholds, different number of standard deviations from the mean. Right here I'm using 3 standard deviations. So standard deviation is a shift or variation from the overall mean of the group. So here we can look at 3. This is very easy to set up and execute. It's just 4 lines of code, I guess 5 if you import the library, right? 5 lines of code, and I run that and I get the salary z-score, and then the IQR score 2. So this is interquartile range, and this looks at the first quartile, second, third, and fourth. Is 4 quartiles, right? And we're looking at the first is going to be lower, the second and third are going to be in between, and the fourth is the highest, right? And this is how we get the quantile right here, 0.25. So anything from 0.25 and lower falls into Q1. Anything 0.75 and bigger, or I guess 0.0 over 75, so 0.76 and bigger goes into bucket 4. And if you're 0.5 to 0.75, it's Q3. So this is the interquartile range, and we have that over here too. Okay, so that's another way to test for your outliers. And then if you look at everything combined over here, we see IQR outlier is showing up here. So these are anomalies. Anything that's true is an anomaly, and it's quite a few of these guys over here. And then if we look at the z-scores over here, so that's pretty high. That person makes a lot of money. Maybe there's a conversation that needs to be had around that person's salary. That is pretty high. This is 4.7, so that's very, very high, $185,000 per year. That's what the guy makes. And this is 4.9. So again, pretty high salaries. These guys are doing okay. And this is all of the outliers too. So now we have 810, right? It's a different method. Instead of isolation forest, that's the first technique we tried. Now we're trying z-score. We have 810 rows. And now to actually get I didn't print the, let me see, let me print that. So this will show me the shape of these two. So the first time we had 992 using isolation forest. Now with the z-score, we have 810. And now using the interquartile range, we have 1893. So just different ways to skin this cat, right? You can pick isolation forest. I like that one personally. It does an excellent job. If you want something just very quick and very easy to set up and use, and very easy to explain to other people, maybe the IQR is the way to go, or maybe the z-score is the way to go, right? 3 different methods that do things 3 different ways. I think they're all working fine, and they're all totally interesting. You just have to pick the best one for your specific use case. There might be a personal preference. There might be a business need why you would pick one over the other. If it's explainability, it's probably z-score or IQR. It's a very simple mathematical operation, right? A couple lines of code, and that's it. This has a standard deviation greater than 3 points away from the mean of the total group. Isolation forest is definitely a little more sophisticated, right? In terms of the overall complexity of the model. And maybe if the stakeholders don't want to deal with the complexity or don't totally understand it and they're not comfortable with that, maybe you have to go with a simpler solution, right? If they're fine, they say, okay, isolation forest, I kind of understand what it's doing. I don't know every single detail of the whole model, but it makes sense to me fundamentally and you're comfortable with it, I would go with that. If you just want something that's very simple to set up and execute and roll out to stakeholders, I would go with the Z-score or the IQR methods, right? So I have some notes down here. I don't think I have to talk about all that. I think I touched on all these things already. So that's it, guys. I'm going to wrap up the video, and hopefully I'll see you in the next one. Bye.